My name is Taiga Fukada from the University of Tokyo. It's a great honor to be able to speak here to you today. Today, I'd like to talk about the integrated model for predicting deformation and cavity growth caused by Coble creep. And here is the outline of my presentation. I'd like to start by talking about the issues. Combustor, such as power plant and turbine, improve their efficiency under higher temperature and higher pressure. But however, such as higher temperature and higher pressure, there's a big problem, creep damage. And this is the example of creep damage. So the key to high temperature and pressure is to controlling creep damage. But there are some problems about controlling creep. First, there's a big gap between the period of practical use and the period of experiment for design. Moreover, there are a few data on the 10,000 hours lifetime, and there are scattering results under the same condition. So the prediction of creep life with advanced or ongoing information is a critical issue. So I next talk about the previous research. First, damage mechanics. Damage mechanics based on the continuum mechanics. However, we need to conduct an experiment under the same condition to represent the effects of damage. So it's impossible to predict the creep damage under the actual operating conditions. The second, micromechanics. Micromechanics deals with the legacy diffusion, grain boundary migration, cavity nucleation and growth, but limited to monocrystalline or extremely idealized polycrystalline. So micromechanics does not reach to predict lifetime of actual structures. The last one is molecular dynamics. Molecular dynamics reproduce the diffusion and deformation at atomic scale precisely, but also limited to the simple grain boundary or non-crystal and short time scale. So there's a big difference from the actual operation period or scale of damage form. So in the previous research, its physics and scale are limited to the respective target areas. So the objective of the research is to develop an integrated mass-scale model for predicting creep damage quantitatively based on frames of materials, crystallography, and some dynamics. So I'd like to talk about the outline of the proposed model. First, under the real condition, higher temperature and low stress, Coble creep is a major controlling factor for creep damage. I explained the Coble creep briefly. First, stress is applied, then diffusion occurs through the grain boundary, and deformation and cavity growth occur, and finally failure occurs. So the grain boundary causes the deformation and cavity growth, so we made two models, a creep deformation model and cavity growth model. A creep deformation model can work alone, so the simulation and validation of only this part is done. But on the other hand, cavity growth model can work with the results of creep deformation model. So we made this coupled model, and the validation of only this part is carried out. So the next I talk about the creep deformation model. Creep deformation consists of static grain growth and dynamic grain growth. Static grain growth is a decrease in potential energy of the grain boundary based on minimum grain boundary potential energy theory. Dynamic grain growth is the grain growth caused by grain boundary diffusion based on the grain boundary relative velocity theory. And this is a formulation of the static grain growth. The formulation is complex, so I explain some important points of the formulation. So as to decrease the total grain boundary energy of this part, this unit, the velocity of each quadruple point is calculated based on the atomic jump model. And this is a dynamic grain growth formulation. Considering the diffusive flux of grain boundary, the relative velocity of the grain boundary is calculated. Based on this velocity, strain rate, translational velocity of the grain, and the velocity of the quadruple point is calculated. And this is model generation. Reproduction of the 3D grain distribution was done by open source software NEPA, and the periodic boundary condition is adapted. And this is a calculation example. The material constant is that of P90 mass steel. And next, I did brief validation by comparison with theoretical formula. And this is a theoretical formula of the strain rate of Coble grip. In this theoretical formula, influencing factors are average grain radius, temperature, stress, diffusion coefficient, grain boundary energy. And changing these influencing factors, we calculated some pattern. And this is examples of changing the grain radius. It is confirmed that the finer grain deforms faster. And this is the calculation result. As a result, strain rate was proportional to -3 power of average grain size. And this is a theoretical formula. So this result is the same as theoretical formula. And for all these factors, good agreement with the theoretical formula is confirmed. And next, we changed other influencing factors that cannot be considered in the conventional theoretical formula, such as aspect ratio. For example, we expand or contract the grains in the direction of stress under the same grain radius. And this is the result. According to the aspect ratio, the strain rate differs. So we can quantitatively evaluate the impact of factors that theoretical formula ignored. And next, I talk about the cavity growth model. This is the outline of the cavity growth model. We calculate cavity growth and cavity nucleation at each grain boundary independently. And this is the calculation flow. After the creep deformation I explained before, cavity nucleation, cavity growth, and cavity sintering and coalescence are calculated and repeat this flow again and again. And this
We got 3 minutes.
Okay. This is the formulation of the nucleation. First, the shape of cavity is this object. This object is the 3D object generated by rotating the path of ellipse. And the number of nucleation is calculated from strain rate. And considering the Helmholtz free energy, the radius of initial cavity is calculated and the new cavity put at random. And this is the formulation of the cavity growth. The function that calculates the stress at each point is found by this differential equation with these 4 boundary conditions. And this is the also formulation of the cavity growth. First, due to the grain boundary diffusion, the cavity grows only in the grain boundary direction. And next, due to the surface diffusion, deformation occurs as the volume is conserved. This is the criteria of cavity sintering and coalescence. Cavity coalescence occurs when the 2 cavities overlap, and cavity sintering occurs when the radius of cavity becomes smaller than the initial one. Then the damage area fraction is adapted for the evaluation index. Damage area fraction is a ratio of how cavities surround the grain boundary. This is the calculation example. This parameter is also P91. And this is the state of cavity nucleation and growth at all grain boundary. The x-axis is angle formed with the load direction. The y-axis is the damage area fraction. Damage area fraction is higher at the grain boundary perpendicular to the stress direction. And this is a picture of experiment. The stress is applied in this direction, and more cavities occurred. More cavity occurred at the grain boundary perpendicular to the stress direction. So this model it produced the experimental result that the damage area fraction is higher at the grain boundaries perpendicular to the load direction. And also, we evaluate effects of temperature, stress, and average grain values. So with higher temperature and higher stress and finer grain, the cavity growth and nucleation is accelerated. Finally, I summarize my presentation. And this is my conclusion. And an integrated multi-scale model for predicting cliff damage quantitatively based on strengths of materials, crystallography, and some dynamics was developed. That's all. Thank you for your kind attention.
Thanks. One question.
Yeah, you have your delta parameter, which is the grain boundary thickness. So just which is in your equations which you are using in the continuum approach. On the other hand, in your model, you are introducing the boundary, my understanding is just the same no matter what is the size of the grain. Does it change with the grain size? Because you said that it is some nanometers, yeah.
Actually, I'm not good at reasoning. Please, could you ask again?
So your thickness of the grain boundary in your finite element model, it was not introduced directly. It was simply a line, yeah, between the elements.
Grain boundary thickness is now constant.
It's constant for all the models.
Yes.
Okay.
Yes. Well, I don't think we have time, so we have to stick to the schedule. So thank you very much.